In this video, we'll talk about the coefficient of multiple determination, r squared, and also something called r squared adjusted. Okay, you've been seeing this r squared adjusted number show up in your linear model output, and it's time to talk about that a little bit, what that is. So first of all, let's review what r squared is, or maybe you've never seen it before, I don't know. The coefficient of multiple determination, r squared, it's the proportion of variation in the data that's captured by your linear model. It is that is, you can think of it as it's the sum of squared. Sorry, it's the regression sum of squares divided by your total sum of squares. So if you draw a picture with, this is a good exercise for you to do. Draw a simple scatter plot with 5 points on the page where there's a loose pattern to it, maybe with an R value of like something like negative 0.5. Okay, so that there's some sort of association, and then draw these sums of squares and color them differently and take a look at their fraction. And then on the other hand, draw 5 points that are very much along a straight line, and you'll see that these two numbers are almost the same. They're almost the same. Another way to think of it is it's 1 minus the sum of 1 minus the error sum of squares over the total sum of squares. So just like the coefficient of determination for simple linear regression, it turns out r squared is always some number between 0 and 1. And if I take the square root of r, I get the linear correlation coefficient. Okay, that's not always very applicable in more general linear models, or certainly in generalized linear models, because r measures the degree of linear association between the two variables, and often, sometimes we don't have that anymore. Maybe we have polynomial regression models that fit a little bit better, but so anyway, r squared equals 0, or approximately 0, implies that the model coefficients are 0, and r squared equals 1 implies that all the data values lie on the regression surface. Okay, including additional variables in the model will always cause r squared to increase, which we will see. Okay, you can keep on adding more and more variables into a model, and r squared will always increase. That is not a good thing, because you can enter variables. You can enter explanatory variables into your model that just don't make any sense. Like, maybe if you're trying to predict the first year GPA for some college students, of course some things make sense, like their ACT score, their SAT score, what they had for breakfast, how much sleep they had the night before, how many brothers and sisters they had, and what their shoe size is. Whoa, no, yeah, but it turns out if you keep on adding these variables, r squared will continually increase. And remember what r squared essentially is attempting to do. It's trying to measure sort of how close your regression surface is coming to all of the points in your data set. So in a sense, sort of, the higher r squared is, kind of, in a sort of way, the better your model is. Kind of. Not always, but that's sort of the general thinking. Okay, so we have to be careful of that. Allowing too many variables to enter the model can lead to overfitting. One remedy to this absurd problem is to introduce some sort of a penalty for introducing too many variables. And this is what we do this is how we get at this. It's with this adjusted coefficient of multiple determination, which we denote with r squared ADJ. Okay. This accounts for the proportion of the variation in the data captured by the regression model, but also incorporates this penalty for including too many variables. Take a look at this. So it's defined to be 1 minus SSE over 1 minus the number of parameters over the total sum of squares over 1 less than the number of data values, which is, these are the respective degrees of freedom. Okay. Another way to look at it is, just algebraically, it's like this. So now look at what happens as you increase the number of parameters in the denominator here. As p gets large, as p approaches n, then this part gets bigger. This part gets larger. Okay, so I'm sort of I'm blowing up that SSE over SSTO. Okay. Okay, so let's take a look at an example. Back to this commercial properties bit. Let's tell you what I'm going to do. I'm just going to copy all of this stuff right out of the notes and just Control C that, and I'm going to drop it right into R and see what happens. It looks like it's going to give me some output there. Looks like what we're doing here is we've got we're going to build a model where we just include the expenses and taxes variable, and then we're going to build another model where we include the expenses and taxes and the square footage variable, and then we're going to build a model where we add to those two variables in the model. We're also going to add the age variable, okay, and we'll take a look at what happens to those R and R squared and R squared adjusted values, and finally compare it to our original output for the model with all the variables in it. Okay, so there we are. So let me scroll back up. I've just done all of those really quickly. Okay, all right, so expenses and taxes. If we just use expenses and taxes to try to estimate our rental rate, then look at our output here for that model. Of course, we've just got two coefficients in that case. We've got, here's our beta naught estimate, here's our beta 1 estimate. Okay, here are our p-values. Looks like they're both pretty significant, or significantly different from 0 anyway. Our R squared value is about 17%, and adjusted R squared is 16%. Okay, now let's enter another variable. Okay, this R squared value is pretty low. I mean, it's really doesn't look like there's much predictability going on there. So now we'll enter the square footage variable. Okay, I think that was this one here. Okay, and so allowing that variable to enter. Okay, it looks like we've got looks like these three coefficients are significant in the model. This is our intercept coefficient, and then our slope coefficient for the, I think it's the expenses and taxes is the third one, and then this one is for square footage. Okay, you can see that R squared has increased. Okay, and our adjusted R squared has also increased, but it's not as high as R squared. Okay, let's add another variable, the age of the structure. Okay, and look at the output. Now I've got 1, 2, 3, 4 coefficient estimates, right? Here's our intercept estimate, and then I've got 1, 2, 3 coefficient estimates for the slopes, and they're all significantly different from 0. It looks like multiple R squared, it has increased even again. Our adjusted R squared is a little less than what it is. Finally, let's look at the full model where we allow all 4 of those variables to enter. What do you get? R squared has increased still. Not very much. It's just gone from 58.3% to 58.47%. So it's just gone up a fraction of 1%. Our adjusted R squared is 0.5629. And it has, our adjusted R squared, you can see, has actually decreased. It has decreased. Okay, from what it has before. If I entered shoe size of the last tenants, this would probably decrease some more. However, this would still increase, believe it or not. Okay, now here's a real naive way of doing this. We'll have a whole chapter's worth of notes on this, but a big deal in regression is model selection. That is, which of the explanatory variables are the ones that you want to include in your model, which ones do you throw away? According to these p-values, you could take this really naive approach and go, oh, hey, look, this variable here, I forget what it is. Even it's what is it? There it is, vacancy rate. The vacancy rate. Okay, the vacancy rate, it looks like is insignificant. So maybe we could throw that out. Okay, well, That's probably okay. That's probably a good judgment. But what you really want to do is try to compare all the different subsets of the variables and check out the R squared values and maybe a few other measures. And just taking this p-value approach to throwing variables out or keeping them in can be rather naive, and we'll address that later. But you want to be really careful of that. But so anyway, the point of this example was to illustrate that in fact R squared will continue to increase while our adjusted R squared value can decrease as the number of variables you enter increases, which is a good thing.